today's talk will be by Professor Anish Arora. I think I'm trying to give an introduction to Professor Anish Arora. I know him through Manik, and I guess as we saw yesterday and past few days, he's an expert in wireless sensing. I think he's worked on wireless networks and sensing networks in the past, right? So in the past 20 years. I think Professor Anish has been visiting Microsoft Research for the last 20 years, I guess. And from what I gather, they've been spent 10 years on collecting, building the hardware ecosystem and the data sets around what he'll be talking today. So I hope we can learn from his experience.
Yeah, great. Well, thank you. Thank you for the invitation. And it's great to be at Microsoft with all these wonderful minds and to meet old friends and run into lots of new folks and great new ideas. By the way, 20 years ago, we started working on device networks at Microsoft. So Bill Gates had his own home network, and different groups in Microsoft were coming up with their own versions. So my research, Human Wang and I were working on device networks, and somehow that attracted DARPA's attention, which got me to working in wireless sensor networks. Before that, I did distributed computing in theory. So building things is something I credit Microsoft to getting me into. So, so yesterday, we spoke about the role of Mote-Scale computing and how it leverages machine learning, and it's poised to leverage deep learning. So today, I really won't focus on deep learning. I'll just pick up on that topic of issues we've run into using shallow machine learning at Mote-Scale. And these issues I'll phrase in terms of this concept of limited signals, which is a vague concept, but I'll try to give you different conceptions of limited signal and how it impacts the design question. Yeah. So just as a recap, Mote-Scale is battery-powered stuff. You've got radios, you're wireless. The consumption of power is limited. It's typically well below 100 milliwatts. You could use energy harvesting. You have one or more sensors. You have one or more processors. So, so just to illustrate the details of one type of mote, here is something that we have been using. For a decade or so, we use systems like these small 8-bit motes, from say TI, and used an operating system called TinyOS, which was a remarkable concept for being resource constrained. And it turned out TinyOS, even though we trained thousands of students, didn't transition very well, quite simply because it was not easy to program. Yeah? So here you have the challenge of addressing low power. And this low power can exploit all these rich low power modes. For example, this Cortex M3 mote that we at Samraksh called the .now mode has really nice low power states. And it's really a software design challenge to be able to exercise those low power states correctly. Yeah? So to address this issue that it was hard to get people to change how they program, we had to revert to a standard programming language. We said we would work in C#. Yeah? So we actually took a system which was built at Microsoft Research about 20 years ago. It's called the .NET Micro Framework. And we took the .NET Micro Framework and we stripped it and we made it near real time, improved its jitter, and added wireless capabilities to it. So what we've ended up with is a runtime that we call the emote, where you can run, at the moment, interpreted and not just in time compiled C# programs. And we get pretty decent jitter. We can program application-specific networks. And the way we do this is by abstracting the radio link as a virtual link. And these could be multiple radios, so all links are offered to the network pattern as a virtual link. And so you can custom design your network at an abstract level. And so with this framework for virtualization and these very general network patterns, we can come up with a rich class of wireless sensor networks. Yeah? So the point I wanted to make was that a mote is largely software designed. In fact, even the sensors are becoming largely software designed. And of course, programming the application at this high level is a convenience that we would like to build on. So Yes.
What do you mean by sensor being software defined?
Okay. As you noticed, I showed you yesterday the radar, right? The radar is actually just giving a simple complex value, right? But this complex value represents the cumulative returns in some region. Yeah. Now, how do I control that region? Should I actually introduce those knobs in hardware and exercise some kind of hardware tuning? Or I can program those knobs in software. So this particular radar has an FPGA, and most of the sensor control is in the software itself. Yeah. And increasingly, you'll find that that's the right pattern for leveraging the sensors, right? This is somewhat counterintuitive, but we keep thinking of digital MEMS as encoding in hardware more and more complex computation. But in fact, sometimes just beginning with a much lower power analog MEMS and doing the rest in software is not only more flexible, but also lower power. So software-defined sensing is the thing that we can build on, although it continues to grow at the Mote-Scale. Yeah? It isn't the dominant pattern, but what we are finding is it's a very useful pattern at Mote-Scale. And of course, all the features that you generate, as all of us are doing, is done in software, right? So we're not assuming that we're limiting ourselves to some features, which are, for example, features like extracting certain filters, which are defined in the hardware itself. We are defining our own features. So by limited signal, what I mean is various things. Yeah. So one of the forms of limited signal is I've got a signal which is rather weak. Yeah. So we are looking at targets which may not be conceptually large. We are in this low power regime where this target compared to the whole scene is rather small. So the signal in terms of power itself can be quite small. Yeah? Now, of course, if you've got an active sensor and the active sensor is battery powered, it's radiating at very low power. Yeah? For example, in the case of the radar, we are radiating energy and the reflections are coming back with a fourth power of reduction. So you've got signal which is quite low in the presence of noise, and the key design challenge is to find how you can represent that signal in a way that you get a good quality of SNR to still be able to do your computing tasks. Now, in addition to the noise being large, the background environment presents a lot of diversity and magnitude of return. Yeah? So we can think of that as clutter. Yeah? So we can place our sensors in regimes where, in addition to the target, there's a large amount of clutter, which is contributing to essentially a form of noise, which we have to reject. Now, sometimes one can make a distinction between the objects in the scene as being targets of interest and targets not of interest. So there might be a distinction between clutter and targets not of interest, and these targets not of interest also have to be rejected. Yeah? So that also constrains your signal. Now, if you get into a sort of a more interesting set of concerns, this is when sensors can interfere with each other. Yeah? So the returns of an object can essentially be interfering. Now, that can happen in multiple ways, which I'll try and outline in the talk. But we'll have to think about how interference affects your design. Now, in certain cases, you might think about this interference as being somewhat constructively or adversarially done, somewhat deliberately done. Yeah. So I'll define this concept called obfuscation. And now the question becomes, how do you leverage obfuscation? Is it a good thing or a bad thing? And of course, it depends on your application and what can you do about that. And a form of obfuscation can simply be spoofing targets by constructively creating fake targets in the scene rather than just jamming the sensor. So that's a very rough definition of the kinds of challenges we run into in applications. And I wanted to spell out how we've thought about it. Really, much of our work is, driven by the application. Our methods are quite basic in some cases, and there's a lot of room for growing this. That could lead to an interesting conversation. So, and the word applications is sort of incorrect. I'll just focus on one application given the time today. Yeah. So the story about why we got into forest protection is really quite basic. You know, in the last 40 years, the wildlife of the world has gone down by 70%. Yeah, and one way of reacting, and it's not just a simple ecological concern. It is also an economic concern. Yeah, there are many dimensions to this concern about how human development is being affected by wildlife reduction. And one way of reacting to that problem is to deal with large mammals. Yeah, large mammals at the top of the animal species hierarchy, you know, have this, not only this attention that gets to people, but in fact, if you're able to tame the damage to them, its contribution to the rest of the chain is quite significant. Yeah. So we ran into problems like in India in 2009, the tiger went extinct in certain parks. Took them a few years to discover it was extinct. They were looking at pug marks and they thought it was there, but in fact they were overcounting the same mark as being multiple tigers. So they didn't realize the decline and they didn't come up as being ready for it. So they had to do things like transplanting tigers. So around 2011, we started this project with a number of partners where I was looking at radar sensor networks. My colleagues at ISC were looking at PIR sensor networks. My colleagues at IIIT Allahabad were looking at a very cool fiber optic based classification of animal targets. Really, really good topic, but that's for another day. So the way this is a baby formulation of the problem. So you've got a reserve or a national park, and in this park, what you would like to do is to see whether people or animals are at points of interest. So there are crossing points where either animals should not be or people should not be, and at these points of interest, you want to detect the activity. Yeah? And in particular, this activity has, in the sense of targets not of interest, has got to reject some types of activity while focusing on other relevant types of activity. So for example, in the particular, so we did one deployment in the Panna National Reserve, which is a tiger reserve. And then we did another deployment in 2016 in an unnamed park in South Africa. This was done with the World Wildlife Fund. And the idea was, here the poachers, when they come in with dogs. And they come in small groups of 2 or 3 people. So you had to discriminate these poachers, but when cattle were going through the scene or goats were going through the scene, you didn't have to alarm the guards. Now, it turns out there is not, to my knowledge, a national park or a forest which is uniformly covered by communications, like cellular. Yeah? It turns out you're lucky if at the guard stations you get cellular or some network access. Yeah. And so we leverage that. Let's assume the guard station is connected. We have these operational points. We want to do this discrimination at the operational points, reach the guard station, from the guard station reach the cloud. From the cloud, contact the management, because guards have to be kept honest. And also, if allowed, contact various social networks. Because a good way of socializing the response to crime is to actually, good way to deal with crime is to actually socialize the response to that, depending on how progressive park managements are. Now, for this system to work, of course, it had to work in this hostile terrain. You've got a low power network which has to cover large areas. These parks tend to be hundreds of square kilometers. Panna is about 650. This park we were in was probably about 2/3 of that. And then you had to make sure that this was easy to operate and to maintain. That's a key requirement, because even though you train the guards themselves have limited technical competence. Cost is an important constraint in the design, because these parks are very cash strapped. And to some extent, the adversary is very intelligent. And it's very organized. And it's very legally supported. Yeah? So you have to be concerned about this being somewhat stealthy, accurate, robust, and reliable. So all these are issues, and that takes us as a motivation into the limited signal case. So here's how we dealt with this. We used this concept of a virtual fence. Although these parks are very large, often the crossings are happening in small linear sections. So for example, in this park in South Africa, there was a remote corner of the park where you had a river which was very easily forded at certain times of the month. Yeah? And there were certain ford points, so there were many strips which were roughly 100 to 150 meters long. So if you could cover these 13 strips, you had covered one major zone. Yeah? Sometimes you have a bunch of watering holes, and poisoning is a form of getting to the animal. So you had to detect what was going on at the watering hole. Alternatively, a third pattern was that there were these ingress routes where people would actually drive in, come in fast, shoot, and head out. Yeah? This is a form of crime which is particularly true in India. Whereas the poachers in South Africa, they were actually coming on foot and walking very fast for significant distances. Yes?
How do you get to know this?
Say again?
How do you get to know this?
All these things are deeply well understood, right? These patterns are well known. In fact, the organization is such that sometimes the villagers are helping the poachers, right? Because of complex social relationships, right? You can harm me, I will not tell on you, but when you're coming, I'll actually feed you for the night, let you sleep and go on. And these patterns are well understood, but it's distrust between authorities and local people. Yeah, that's one major source of contention here. Yeah, the other thing is, I'm not suggesting technology is the answer to this big problem. It's a very small element at the bottom of the response hierarchy, but it's a necessary element, and that's the part that we are focused on. Yeah. So here is just to get you to visualize what's happening in South Africa. So it's about, I would say, 5 or 6 kilometers from this river area is a guard station. The guard station's on the top of a hill. It has this tall chimney. On the tall chimney, we've got a base station going. Yes. Now this base station has got line of sight visibility to a bunch of abutting hills. These hills could be 2 kilometers, 3 kilometers, 4 kilometers away. So we can create single low power links to them. These routers to which the first hop links are could be put on poles, they could be put on trees. And now at these tops of these hills, we somehow have to go down into the valley so that we can communicate with the sensors which are placed along the river. Yeah? The sensors are, yay scale, size is not an issue. We didn't really have to go much smaller. And in fact, perhaps in our earlier deployments, we even had this size, right? So you can mount these on little branches, on little trees, and you put them at a certain height. You don't want the radar, in this case, to be at ground level. But here we had a solution which was roughly on this form factor. Now, a little bit of a backgrounder on how radars work. So essentially, this is a micro power Doppler radar. So it's not a continuous wave. You're shouting out pulses, right? Pulses are sent at a high frequency. You can send them 1 million or 2 or 3 million times a second. That's the pulse repetition frequency. Yeah. So this is a very old concept of radar, which is called homodyny radar, that when these multiple pulses, this is an example of a single pulse, is shouted, it travels to the target, the reflection comes back, and the reflection is convolved with a duplicate of the transmit pulse. Yeah? And that convolution contains the information that you're looking for. So we are running at what might be a few percent of duty cycle of a continuous wave, and you're shouting out something that's very low power. So the overall power consumption is not too much. Yeah? That said, this is the biggest consumer of power in our system. Over the years, we've had many versions of the radar. We started off with 30 milliwatt, went to 40 milliwatt, and finally have been able to pull that back to around 16 milliwatt. And we think we have designs which will go down to a couple of milliwatt, but that's going to be real research. So you have this big power consumer, but still in the low power regime, which we are going to analyze our information from. And here I spoke to this a little bit yesterday, but what you have is this complex return, and this complex return, as the target approaches, has this particular pattern which grows stronger, and the phase rotates. and the rotation of the phase gives you a sense of how much distance is traveled. Yeah. So this by itself is an interesting feature to begin with. So if you look at the nature of the clutter response, which is all these bushes and trees around the radar, are actually not producing much change in phase. This phase is self-canceling, but if a human or a target not of interest goes through the scene, that is a displacing object, something that's not moving in situ, and you can see that there is a significant change in the phase, which we can track. Yeah? So you've got a basis for starting on discriminating objects. But if you want to get finer grain, then you can look at not just the amplitude and the phase signatures, you can look at the time frequency signatures. So here are signatures of how a car, which is a rigid object, corresponds to a very narrow band of excited frequencies. Yeah? But the human and a dog, which is a soft target, have this much richer frequency spread. And within this frequency spread, although not very nicely visible at this resolution, are very interesting microdoppler patterns. You can see not just the torso, you can see the limbs, you can actually discriminate the arms and the legs. And in fact, that becomes a basis from discriminating from the dog, because the feet typically are much more spindly, and therefore you don't have much return from the legs.
Is this a spectrogram of the phase shift? So you look at the phase shift with time, and this is
So this is frequency, right? And what we are seeing is the frequencies which are excited over time, right? So the
Doppler shift.
this is the Doppler shift, precisely. Yeah. Yeah. Now, how do you classify? I will not spend much time on this. You track the displacement, and you can reject things which are moving in situ based on that previously explained idea of how the displacement unwraps, whereas in situ movements do not traverse much distance. And then you run this support vector machine, which leverages a bunch of features that we have designed. And it took a while to lay out something like 80 features. Here is an example of a feature which says that what is the area of excitation above a certain threshold in the spectrogram. Yeah. And so for a dog, that anomaly area is much smaller than for a human target. And we hope this is an interesting feature. We have no idea whether it will work. We throw data at it, and we look at the relevance of these features, how much information gain they have, and we try to select features. And then we, of course, implement this, and details of that are not relevant at the moment. Any questions before I really begin? Yes.
You have to recalibrate the sensor.
Oh, so this is the story I would like to tell in the next few slides. The aspiration is I will collect data from multiple clutters, multiple backgrounds, on multiple targets, on multiple instances of radar of different generations, and come up with a classifier that works for all. That's the aspiration. Yeah? And the story I'd like to tell is, well, which parts we succeeded on, which parts are still moving. Yeah? But the brief answer is, for the longest time, we've stuck with one classifier for all environments. Yeah? That's the thing we're working towards. Yeah? Okay. So let's begin by saying, well, clutters are very different. Yeah? So here is the response in terms of amplitude. Sorry, this is hard to read. Amplitude of grass, amplitude in a more idealized setting where one would imagine there are no reflectors, like just tarmac. Yeah? This is an airport where we do experiments for DARPA. And here is the change in phase over time. That axis is called rotations per second. So the unwrapped number of rotations per second gives you a sense of how phase is changing. And as you can see, these are significantly different in both the amplitude and the phase domain. I don't know if it's absolutely visible, but they are. Yeah? So now the target returns will be superposed on these variable clutter returns. And the thinking is, it's possible, if you've collected in enough diverse environments, to estimate a worst case background clutter, and to choose a displacement threshold for targets in these background clutters, which will lead to a constant number of false alarms. So the false alarm rate will be constant. So we want to allow something like one a month or one a year. Yeah? And that at this point of description is feasible. Yeah? So I'll give a chart to that momentarily. That's a simple explanation. The more interesting explanation is you would have thought that grass is, there's more clutter in grass than in the idealized concrete. So you should have had higher noise in the grass case. Turns out it's the opposite. And a lot of that has to do with the implementation of the radar, the particular choice of the components, and how the intermods, et cetera, get affected by these targets. So in fact, concrete is an environment in which the phase noise drifts, whereas when there is more clutter, the phase noise actually tends to become quiescent. Yeah, counterintuitive, but again, something unanticipated. Now, if we just step back from clutter and just look at the underlying board noise, the underlying board noise itself has varied significantly across various generations. So this is a very recent radar, the 16 milliwatt radar I was referring to, where the median of the amplitude, this is just plain simple noise, is this number 10. Yeah? Whereas the radar that we put in South Africa, the median of that is substantially higher at 72.4. Yeah? And conversely, when you look at the rotations, you'll see that the noise rotations are higher for this radar as well. So for different radars, we have to be able to tolerate this underlying noise. And the way we do that is by doing an online estimation of the background noise. Yeah? So you maintain this estimate of the background amplitude. And what you say is, I'm going to choose some number that I have learned, yeah? some estimate, some functional estimate of the background noise, which if it shows up in a return, I will treat that as noise and I will reject that sample. So I'm actually going to be throwing away samples which correspond to what I am hypothesizing is a noise return. Yeah? Now the net effect of that is that of course you're actually throwing away some signal returns. You've got soft targets. The soft target amplitudes will vary. Some of those soft target returns we will throw away. Yeah? So we are going to underestimate our displacement. And so the learning of the displacement threshold now gets coupled with the sample rejection threshold. Yeah? So around 2010, what we found was that in many environments, if this is like an empty field, there's a parking garage, there are lots of trees, grasses, different places, and we found that a single threshold could give you this constant false alarm. But as we went to generations of the radar where the noise grew a lot, that gave us a displacement threshold where we started to have false negatives. So we had to introduce this concept of background rejection. And after we do background rejection in all of the environments we've collected data on, that technique will work. Yeah. So we've come up with this online algorithm for estimating the noise and seeing what and having trained for various levels of noise, for various levels of rejection, what the threshold is going to be. Yeah.
What's the plot there?
So here, what we have is a log scale which says the probability of the false alarm as a function of the distance that is traversed. Yeah. So what this is saying is, if you look at a case where you have trees, the probability of the false alarm drops more quickly. So in order to get in order to reject tree movement, a threshold of 0.17 meters would have been sufficient to give you a probability of false alarm which was significantly less than one false alarm a week or one false alarm a month. Yeah? But you'd have to use a larger threshold to reject whatever this parking garage one is. Yeah? And so as the noise increased for us, this threshold that we had to reject became something like 0.65 meters, and that was competing with what actual displacements on targets were. So we would have gotten false negatives. Yeah? So in order to rein in the false negative, we introduced the background rejection and then chose this universal threshold that here, what we are saying is something like 0.4 meters is sufficient to reject clutter in these different environments.
So this is the phase shift over a certain period of time.
Yes.
About 10 seconds or so.
Yes. This is the phase shift Um,
Wavelengths, I guess, in wavelength.
yeah, in rotations, yes, yes. In a window, exactly, precisely. Yeah. So the window, of course, is dictated by the windows that we use for discriminating displacement, right? And there also, we've got to build in the fact that our targets are not moving continuously; they pause. Yeah, they will change orientation. So we have to introduce some techniques for handling those cases in those windows. So in fact, I suspect those ideas may be relevant for you, but we can take that offline. Yeah.
Environmental factors like rain, humidity, that might also.
Yes, this data set includes high wind, presence of rain, moving water nearby in the scene, etc. Yeah. So this is painful, right? We have to collect all this data. Yeah. Now, so to get to Shishir's question, the question is, how do you design a classifier which works in a new environment, which you haven't encountered before? And the very simple observation is try not to train from data collected in similar environments. There is a real gap between the performance that you expect to get between a system which has been trained for different environments versus a system which has been trained in similar environments. Yeah? So we started doing designs where we are looking at what the cross-environmental information gain of a feature is. Yeah? And that leads to this very simple idea, but maybe I'll spell it out. So here is a feature which is not robust. If you look at frequency noise and you look at the volume of frequency of the energy in this spectral domain above a certain threshold, that can change quite substantially. So it's not a robust feature. But if you look at, just project that area of that object of that spectral power of activation above a threshold into the area or the shape of that activation, then that seems to be much more robust. So we'd like to find in our feature selection not just features which have high information gain, but which are likely to show very low variance across different environments. Yeah. And so that led to this work where we came up with techniques for starting off with things like MR information gain or information gain, but then actually pruning out those features by adding this dispersion component, which we called the mean absolute deviation. And we are trying to basically minimize this variance, and that's modeled by throwing in this hyperparameter, which takes into account the relative importance of the information gain and the variability. Yeah. So roughly speaking, the very simple idea is choose those features which are going to have low variance across environments while not losing information too much. Yeah. So that's the answer to your question. Now we run into cases which are more interesting. Okay? So the first case is a case where assume that the pulses generated by a radar are periodic. Yeah? Assume accidentally the pulses generated by two radar are perfectly aligned. Yeah? Now the return of a target from radar 1 might show up in the reference pulses which are convolved for radar 2. Yeah? So now targets which are potentially not even in the scene of radar 1 are not in the scene of radar 2 are showing up because radar 1 is exciting them. Yeah? So that's a problem that shouldn't be allowed, right? Normally we don't really place radars very close to each other. If I'm counting the number of people in this room, one radar should be sufficient. But if there's a neighboring room which has its own radar, the question is, am I seeing the targets there in my return here? Yeah. And the way you typically handle this is by desynchronizing the pulses. And that's where software control becomes helpful. Yeah. So how much randomness you want to create, what patterns you want to create becomes something that you program. Now, another topic is as we get to it's one thing to say a single target displaced through the scene and the phase unwrapped nicely, but what happens if multiple targets are in the scene? Yeah? The simple case is when one target is somehow dominant, it's close to you, and essentially what you are tracking is that one target. But if there are cases where you want to count and the other target is behind the dominant target, how do you discover that? And so we did some work on counting classifiers, actually regression functions for counting, where the very, very high level summary is, first of all, the longer you observe, the more likely the obfuscated targets will reveal themselves. It's kind of counterintuitive, but it took us a little while to discover that. And the second one was that there are certain features where you can look at, shadows of objects, hidden imprints of objects. So we discovered the need for looking in the spectrogram for gradients. So you had this strong return, this area of excitation, but you also saw that there was a smooth, not too sharp gradient besides it, which was indicative of some other objects which were there. And so you started using those gradient features to build your estimates of the number of people. So here is so any questions on that idea? Really, these are separate pieces of work, and I'm not explaining them at much length.
So,
yes?
So in the case of cross target, do you want to figure out all the targets, or you just want to say that there is one target here?
Yes, it depends on your application. So in the sensor I was describing for this room, that's really about counting the utilization of the room. So we can do various things, we could decide how much air to pump through a room based on its utilization. Yeah, and that's an energy saving. So yes, sometimes you really do want to count the number of targets. Another example is this bike pedestrian network that we are deploying, where we want sort of multiple points of utilization across a trail network. Currently, that's not very well handled. What you have is data from phones, right, where people who are going through those trails are self-reporting, but you don't know what fraction of the population is doing that very well to build your estimates. And the other technologies are quite manual. So the planning in a city like Columbus is largely based on trying out some technologies, but actually depending on human counts done twice a year to estimate which trails are being used, which ones to fix, et cetera. So we'd like to actually do low-cost counting at multiple points in the trail network. And here, this problem of obfuscation is basic for us. Now there is a different form of obfuscation which is somewhat privacy-centric. So here I'll be describing radar-like classification, but I'll be doing it in the traditional comms domain. So in the recent several years, there's been a bunch of work where people have looked at wireless signals, and you look at the side channel of the wireless signal in some sense by extracting the low frequency components of the signal out of it by integrating a number of samples. And so just like we were using a basis for recognizing that there was a target in the scene by a radar, you can look at the Wi-Fi comms which are reflecting off this target to discriminate, is there a person in this room? Yeah? Or how many people are there in this room? Now supposing I want to hide the fact that somebody outside can observe, outside my house, can observe whether somebody is at home or not. Yeah? How would I do that? Yeah? So that's this concept which I call obfuscation. So the idea is something like this. If you look at what this is the signal being transmitted, this is the signal being received either at the Wi-Fi receiver or at your sensor. That depends, that has these 3 degrees of freedom. So the target influences the amplitude, it influences the Doppler shift, and it influences the propagation delay. Yeah? So I have these 3 degrees of freedom, and I don't know what sensor this is going to be used, but the sensor is somehow going to use some combination of information in these 3 degrees of freedom. Yeah? So what I would like to do is to somehow obscure the information in these degrees as follows. Yeah? So what I'm going to do is to introduce yet another node that I call an obfuscator, which is going to transmit copies of the incoming signal. Yeah? So this signal is being sent in parallel to the transmission signal, right? So it all has to be constructive in some sense. So we are using for this obfuscator an implementation which is based on full duplex radios. Yeah. So in this copy that we are going to relay, we are going to perturb in these 3 dimensions. We're going to perturb by adding an amplitude component. We're going to perturb by adding a potentially different Doppler component and a different phase component. Yeah? And so the net result is that instantaneously we can distort the amplitude and the phase. But it turns out that in the frequency, that is still discriminable. And in order to compensate for that, the rate at which you distort becomes relevant. So as long as you're distorting at a rate which is faster than what the sensor was trying to use, then you should be sufficient. Yeah? There are some very interesting details about how the full duplex deals with self-cancellation, which I'm not going to talk about. But the interesting thing is this: an obfuscator can itself prevent a sensor from working while itself being able to sense. Yeah? So we can create legitimate sensors while simultaneously obfuscating illegitimate sensors, yeah? Without, by the way, affecting communication, and that's a whole other story. Yeah? The communication rate, in fact, doesn't go down, it goes up because we are, in fact, relaying. Yes?
So can poachers also use similar sensors?
Yes, of course. Yes, of course. Yeah, so this is always a cat and mouse game. And this research itself is pure cat and mouse because I'm talking about a single sensor, a single antenna sensor. If you've got a distributed array of observers, then this technique per se is not sufficient. We have to move to the next level in that game of obfuscation. Okay. And so here is sort of showing how as you introduce distortions in copies, what happens as the granularity what happens to the granularity of the spectrograms as the Doppler shift changes. Yeah? So this higher rate of change will give you a result something like this. Let's assume this is the pattern that the sensor was looking for. After obfuscation, you've essentially removed the components in every part of this so that that pattern should no longer be discoverable. So we gave implementations of iCloak and we showed how they performed in at least in the lab setting. Yeah. So an interesting comment there is much of the technology, actually, it's harder to make it robust across different environments for sensing, but it's easier to obfuscate it. That problem is easier because all I'm doing is I'm being destructive. Yeah, in the sensing domain, not the communication domain.
So even the radars can be attacked using this?
Yes, this is all RF, right? Yeah, and in a radar, you can actually do something similar, which is you can inject signatures. So if I know what signature is to be expected by a sensor, I can pretend that there is somebody in the room by spoofing that. Yeah, my obfuscator can now become a spoofer, and this is an example of a lab of a measured spoofing to show how you could emulate a particular gesture like a pull. So the last topic I'd like to focus on in terms of limited signal is how do we deal with the lack of data. This is a problem we all face. We go around buildings in different ways and collect information, malls, forests, etc. But it's really, there's a lot of problems in this process, and most importantly, it's inefficient. So the cost of this process is quite high. Yeah? So in Chandigarh, we collected data on tigers and bears and I forget the third, elephants, yeah. This may be Madhya Pradesh. And we didn't get fantastic data at all. Tigers are very lazy in the afternoon. Yeah? You don't want to collect data on tigers in zoos. Yeah? So we really, for building a tiger versus human classifier, I need data from elsewhere. Yeah? And the impact of not having data is quite simple. Here, for example, is, you remember the phase chart I showed you for a human and a ball, right? Here is the time frequency component for a large ball which is seen close to the radar versus a human that's quite far away from the radar. And from a pattern perspective, they look quite similar. So if I didn't have sufficient data on weak humans, this classifier would likely have made a mistake. Conversely, what we find is that sometimes a single parameter for our features is not enough. You need multiple parameters for your feature to actually capture the variability of targets. So to be able to capture both the strong ball and the weak ball, I might need multiple parameter instances. And if I don't have a rich enough data set, I don't capture that fact. Now, the problem is almost wicked because your targets are quite variable in size. They actually walk quite differently. Men and women and children walk differently. Their speeds tend to be quite variable. Their trajectories are quite unknown. They could be stopping, turning. Dogs like to just go around in circles, and that's having a good time. And their activities while they're doing this can be changing quite a bit. So you need that variability built into your data collect. Now, what's sort of worse is the problem is almost inverted because we've collected data from radars which were placed, as I was telling you, at about 3 feet. But what if a radar is placed at 8 feet, right? Because in the vertical dimension, it's a 30-degree angle. And so the response that you would get would be very elevation dependent. The orientation of the radar matters just as well because it aspires to be an omnidirectional sensor, but it is not exactly one. It has got strong front lobes, somewhat strong back lobes, and weaker side lobes. So the gain in different directions is different. As I told you, the noise characteristics can be different, and across builds, the wavelength can be different. Say why? Yes. It aspires to be an omnidirectional, but it has artifacts in it. So even the central front lobe is somewhat left-leaning, right? So it has to do with sort of board capacitance effects and all of that. And how well impedance matching is done. So what we would really like to do is to augment our data synthetically. And I'd like to describe our evolution in augmenting data, starting from something trivial to something more interesting. So here's a trivial idea to get the stage set, right? So the radar is not exactly omnidirectional, so you've got different gains. So if I have a radar file of a target going on a radio where I know how much its gain is larger than another radio, so this is controlled data, right? Where a human is walking along a certain radio. And if I just simply if I vary the gain, I can produce the same behavior on a different orientation. Sort of a trivial idea. Now, slightly more interesting is that if I focus on the target who is walking with a uniform speed, big if, then I can come up with a data set which works at a different speed by actually upsampling or downsampling. That turns out to be conservative. This one, as we test in training, it is slightly less useful than the previous one.
Suggesting that I take the signature, the radar signature of a walk at a certain radius, and use this model to imagine what it would look like if someone is walking at 10 meters away.
Precisely.
Or
yes.
Are you suggesting that you generate synthetic data from scratch?
No. So we are starting off with a data set, some of which is controlled and well labeled, and we are using that data through these primitive models, and they are primitive, trust me, to generate other data. If you generalize this idea, and you've got walks in different directions, some along radials, some along orthogonals, different radials, you can synthesize pieces and come up with arbitrary trajectories. So you can come up with a richer data set, which is what this last one was trying to spell out. And in the interest of time, I won't spell it out. It's really very simple physics. Actually, this stuff is not great at all, right? Because a lot of our features are looking for microdoppler. I modeled how the gross body speed would show up in this other walk. But what about the microdoppler? What have I done to it? I may have actually distorted it in a way that was counterproductive. Yeah? So what this has led us to is to rethinking how we generate our synthetic data. And so what we are doing now is to say we need a source where we have well-labeled data from a co-sensor. In this case, what we are doing is, we have video, which is giving us, these temporal sequences of labeled information. Yep. Now, then what we would like to do from this, this co-sensor, we would like to extract from that the positions, the orientations, the sizes of the various components. And then from that, we should be able to generate via radar simulation models our traces. Yeah? So to keep this somewhat basic to begin with, we start off with video. From that video, we extract position, orientation, other information. And then we feed that into knowing all the components of the foreground and perhaps some components of the background. We can superpose all those returns and come up with the radar return, doing something like that in a radar simulation toolbox, MATLAB. Now, that idea itself can be made a little bit richer by throwing in various model parameters. So here, even the video has been captured at a certain height, at a certain orientation, often from a fixed camera. But I want to try various other orientations and elevations. So now I can augment the model that I'm using for generating the radar data and create many more simulations out of that. Yeah. So somewhat pictorially speaking, we had two approaches to collecting video data. One is to using this motion capture. Motion capture, you actually get data for humans, for dogs, for vehicles. This is somewhat publicly available. Sometimes you have to pay for it. Yeah? So this is nicely labeled data where you've got the body components marked in it from which skeleton data can be extracted. Yeah? And similarly, even with the Kinect, you can come up with skeleton data. Now these joints can be converted into can be treated as the ellipsoids, and you can estimate the limb ellipsoids for that. And that can be used to generate your radar simulation. Yeah? Conversely, you can decompose the video into polygons. And for each polygon element, you can look at what its response is going to be and superpose those responses in your radar simulation. Yeah? Now, having generated all that, that data, you can now try creating other model instances by throwing in the parameter variations from some set and come up with a richer set. So now we're at the point where we are looking at the accuracy of this richer generation. It looks quite promising. And coming into this workshop, we had this debate about whether we should use synthetic data or not. And we think we're not using it now, but we think we should be using it because it is accurate enough. Okay, so that was the story I wanted to share about limited signals. And roughly, I'd like to conclude by looking ahead on where we ought to be focusing. So one thing to ask is, we've had these somewhat primitive ways of dealing with limited signal for shallow learning. But these issues are going to be handled, must be handled in the deep learning work. So how does deep learning provide us a good basis for handling limited signal issues? Bunch of questions there, I think, which should be interesting research. But the other thing that we have learned, and this goes back to Shishir, your question, is it the right thing to learn a classifier that works across all backgrounds, that works across all locations, that works across all radar technologies? And we are coming to the point where that's not the right answer. So we'll have to specialize the sensor based on its type, based on its location, and some of this is going to involve online learning. Yeah? So of course, we need a basis by which sensors can share their model drift with the cloud, and the cloud can come up with new general models for everyone. Or more interestingly, you can do federated learning. So what we are running into a case is while every sensor is estimating its own background, it needs a basis for being able to relearn its model. And that can be done locally and or assisted by the cloud. So what are the patterns for that? So those, I think, are going to be very interesting for limited signals. So with that, I'll be happy to take questions.
So can you talk a little bit more about this federated learning? So, like in what setting are you thinking about it? Like in the HornNet setting?
No, actually SONYC. So I'm, yesterday I spoke about this Sounds of New York City project, which I didn't have time to explain today. But the situation there is you're placing sensors in very different parts of the city. So some can be in urban canyons, some can be in city parks, right? Some can be in housing areas which are, a mixture of trees and low buildings. So in all of these, the propagation characteristics will be quite different. It turns out we do have information about these different parts of the city which can be used to model how sound will propagate. So we have folks on the data analytics side and the visualization side who can tell us what we think propagation characteristics would be. Yeah? So that can be given as input to your cloud learner. Yeah? But the other question that we can ask is, how can a sensor at a given location notice that things have changed enough foliage has changed that my model is no longer working and become a basis for triggering? Yeah? Or can a sensor benefit from sharing its, what's the right word? Let's call it mode. Yeah? I hesitate to use context in this case, right? So we could have our classification outputs be done for different modes. And can a sensor provide its mode to its neighbors as a way of informing them which might be the relevant classifier to use? Yeah. So we are basically exploring a number of options for handling the drift of the model of a local sensor. Yeah. And one thing that I'm trying to do is to provide the plumbing to support that learning, right? So we're reserving enough energy budget for sharing data snippets which are indicative that my model seemed to have low confidence in assessing this particular data item. So how does this inform the learning of the regional or the global model?
But do you really need to do it an online learning question? Like, can't you maybe collect data for day or 7 days?
Yes.
And then learn a specific model for that?
It's quite possible. Like I mentioned, we have 30 years of data. So we have data from, let's say, 50 to 100 locations, which are telling us over 2 years how the sound characteristics changed. So assuming that data gets labeled and that labeling is trustworthy, perhaps that can be done. Yeah. Yeah. Now, how predictive that is of next year or next spring, I don't know. And that takes me down this road of actually just being able to recognize what mode I'm in. Yeah? If I can recognize what mode I'm in, I can see which classifier to bring in from a library of classifiers. Yes?
So with regards to the changing environment scenarios, right? Since you're working in the RF domain, can't we use the same technologies for channel estimation that's used by cellular providers?
Okay. So I'm still trying to parse your question. So perhaps I can talk about the difference between cellular modeling and low power RF modeling as a way of starting the conversation. So very good planning tools exist for how cellular characteristics will be across a region, and they can tolerate topography quite well. And it's probably because they're in a different SNR regime. Yeah? When we try to use the similar planning ideas for deploying our relays in South Africa, it turned out that we were quite bad in estimating what would work. So let me just illustrate that. So in a low power regime where you can very quickly go from constructive to destructive interference, moving a radar by 3 or 4 feet, actually half a wavelength, can take you from constructive to destructive, right? But what we found was that I had to search in that region to find a spot where I could deploy my radar. Yeah? So one would have predicted that going down a hill with this medium amount of vegetation should have given you 300 meters of range. But that was not enough. Then you had to do the search, which was extremely painful when you're climbing trees. Yeah? So I don't know how easy it is in this low power regime to do what you're saying. Yes.
How easy is it for you to either camouflage or mimic an animal?
Well, you know, for years I had my boys trying to behave like dogs when we were collecting data. It is not really easy. Yeah. So I'm going to sort of distort your question. The question is, how would you fool this radar? What are the ways of fooling it? So one way of fooling it is to actually move extremely slowly. So when you look at special operations people, they can sometimes move a meter an hour when they're crossing very sensitive borders, right? This thing is sensitive up to 2.6 centimeters per second, right? But a meter an hour is much slower than 2.6 centimeters, so you're obscured. Yeah? The other thing you can do is to be extremely fast, right? So the way the filters on the radar are set, you can pick up this 2.6 meters a second and really about 5 meters a second. But it's possible to run faster than 5 meters a second as a way of avoiding this. Yeah? You know, we are banking on the fact that this poacher is going through this densely wooded, forested scene, right? Through these narrow trails. He's actually coming in through this hidden way and will get picked up. But if you're doing the same thing with cars, this probably will not work. Yeah. Yes?
To what extent does cross radar interference actually affect your performance? Because it need not always be constructive, right? It could be the other way around as well.
Yes.
So
Yes.
like have you made any observations of how it's impacting?
Yeah, you know, it has not affected us significantly. Yeah. So what I'm reporting are cases where we've deployed sensors far too close, where we see a little bit of observation of a target even before it enters the scene. That observation is not very predictable. Yeah. So sometimes it looks like a clear target, sometimes it doesn't look like a clear target. Yeah. So what I'm saying is that this is not a major problem for us in practice, and it's a manageable problem, in part because we program things. As it is, it's a very low probability that the periodic pulses will line up, right? And we're also throwing in randomness, and randomness is good because it makes your radar stealthy, right? So it's harder to see the pulse pattern. You need a higher order detector to know the presence of the radar. So yeah, for us, it hasn't been a major problem, but we are seeing instances of this in our training data. And the question is, how much is it affecting our training data is what we are trying to establish right now. Yeah. So my interest is in seeing if I can classify it and prune it so that I'm only learning from clean data at the moment. Yes?
What are the biggest sources of false alarms that you encounter?
Okay, good question. So I think the biggest source of false alarms has not been environmental, it's been radar design issues. Yeah? So if you've got a radar which has got unusually high noise, and we haven't gotten the thresholds right for that, right? That's where the false positives tend to occur for us. Yeah. Oh yeah, maybe I should give another example. So the World Wildlife Fund tested our system, which was doing a human versus a cattle classifier. And they took it onto a horse farm and they tested it with horses. Yeah? And they said, yeah, I'm seeing humans all the time with horses. Your system doesn't work. So that I don't know how to parse. The system wasn't designed to discriminate horses as horses. Yeah? So that has caused some confusion, right? So if we are deploying this in an environment where we've trained for cattle and goats on one side and humans and dogs on the other side, and all of a sudden this rhino starts showing up, we don't know what's going to happen, right? So that can be viewed as a false positive in the system. Yeah. So that operator issue we have today. Yes.
Were you only classifying the signal, or were you also detecting the distance?
Okay, this is not a ranging radar. Yes. So what it lets you do is to look at the relative distance, not the absolute distance. Okay. Now, if you could do very coarse localization, because for example in Panna the way it was set up was we knew there was this trail coming in close to a village which went a certain distance, so you were actually putting sensors along the trail. Yeah? So in that setting, you already know where the nodes are located and you're within a few meters of that, and that is sufficient. But more importantly, you've got actually multiple sensors observing, so you can be more exact if need be. Yeah. But yeah. So conversely, there's a lot of research on very accurate localization with ultra-wideband radar. There's a lot of literature on that if you're interested. One of my students, Prabal Datta, has written some papers on that.
Can that be done by GPS triangulation, like similar to triangulation where you have distances from the radar?
Yeah, you certainly can, and it costs a lot of power. GPS will take you.
Not GPS, but the same thing with AR.
Yeah, triangulation is certainly the way you handle localization. The question is, how do you get your range estimates? So you can go to a ranging radar. And one reason we introduced the FPGA was so that we could create very narrow range gates. So right now, the way the radar works is roughly 1.5 meters from the radar to about 12, 13 meters is everything there is treated as one response. But you can create range gates which are about 1 meter long. So now you can create 12 such range gates, and you can sweep the radar through each of them. And then you can localize within that distance, right? But that's a 1 meter, it's about a 0.5 meter error, right, on average. Whereas what folks in localization are trying to do are to get sub-centimeter localization accuracy. So that's a slightly richer, that's a harder problem.
What is the frequency band?
This is centered at 5.8 gigahertz. It's a medium bandwidth, so it's about 100 megahertz bandwidth. Yeah, so it's not an ultra-wideband radar, but it's still got rich information. Yeah.
Any effect from the ambient radiation from Wi-Fi?
That's a good question. We have significant experience with that. So we coexist with Wi-Fi and Bluetooth without being affected. Yeah. Yeah. Okay. Very good. Thanks a lot.